Okay, so let's talk about periodic trends. So periodic trends tell us about the reactivity or the properties of different elements based on their location on the periodic table. So there are 4 periodic trends that we are going to discuss, and I'm going to draw kind of what the periodic trend is here on my periodic table. So let's start with something called ionization energy. Okay, ionization energy. Ionization energy is defined as the energy required to remove 1 mole of electrons from a mole of gas phase atoms or ions. So it's essentially telling you how much energy does it take to remove an electron. So we know that the noble gases over here in group 8 are the most stable, meaning they have a full octet, they have the most stable electron configuration. So if you wanted to remove an electron for something over here, it would be extremely difficult because these already have the most stable, most desired electron configurations. Over here, it's really easy to remove an electron because these in group 1 and 2, they want to lose electrons so they can be stable like their nearest noble gas. So the trend for ionization energy is that ionization energy increases as you go across, and it increases as you go up. So it increases as you go across a period and up a group or family. So this up here would have the highest ionization energy, and these down here would have the lowest ionization energy. So some things that you might see on the SmartWorks homework or on an exam is I might give you a list of elements in order, either in the same period or in the same group, and ask you to put them in order of increasing ionization energy. So based on this trend, as the ionization energy increases from least number of electrons in the outermost shell to most number of electrons in the outermost shell, and from most shells of electrons to least shells of electrons, you could put them in order of increasing or decreasing ionization energy. If I ask you to explain the trend of ionization energy, what would not be acceptable would be because it's to the left or the right or because it's above or below. What would be acceptable is saying the fewer number of electrons you have, the easier, the least amount of energy it would be to remove those electrons. The more number of electrons you are, the closer to having a full octet, the more energy would be required. So the energy required to move an electron is what ionization energy is, and this trend shows you that it's much harder to remove an electron from an already full octet than from an outer shell that only has 1 or a few electrons. The less number of electrons you have, the more energy it would take to remove an electron. That's why it increases as you go from a high N to a low N. So it has to do with the number of electrons in the outer shell. And it has to do with the distance between the nucleus and the electrons. Because remember, the nucleus, that's where the protons are, and the outer shell, that's where the electron that you would be removing is. Okay, so the next trend that we'll talk about is something called electron affinity. And electron affinity has the same trend, but it kind of has a different definition. So I'm going to write electron affinity. So the electron affinity is the energy change that occurs when 1 mole of electrons combines with 1 mole of atoms or ions. So the electron affinity could also be kind of defined as the attraction of an element for an electron. It's the affinity to add an electron. So it also has the same trend. It increases across the periods and it increases going up the group. These elements over here, except for the noble gases, which are not included, but everything on here is going to be more interested in gaining an electron. Over here, these want to lose electrons. So that is the trend for the electron affinity. It's the same as the trend for the ionization energy, but for different reasons. The next trend that we are going to talk about is called atomic size. Atomic size is just the size of the atom. Atomic size depends on two things. It depends on the number of energy levels, and it also depends on the attraction of the electrons to protons. So how far away are they? So the trend looks like this. So something right here would have the biggest atomic size, something up here would have the smallest atomic size. So the number of energy levels, as we increase energy levels and we're adding shells of electrons, that's going to make, for each shell, it makes the atom bigger and bigger and bigger. The attraction of electrons to protons means that as we go across the period here, and we are adding more and more electrons, if you're within the same shell and you have 5 electrons and then the next one has 6 electrons, there's a little bit more attraction between those positive and negative charges. So you still have the same number of shells around that central nucleus, but the more electrons you add, the tighter and tighter and tighter that gets squeezed. So within the same period, as you get closer to the noble gases and you have the most number of protons and electrons that can be attracted to each other, it just squeezes it a teeny bit so it's a little bit smaller. So something down here would have a bigger atomic size than something up here. Sometimes instead of atomic size, you might hear this called atomic radius, which is essentially the same thing. It's just a different term for measuring the size of an atom. The last trend that we will talk about that you can't really base on the periodic table is ionic size. And you would be comparing the size of an ion to the size of that atom. So you can't really compare two different atoms, two different ions to each other, but you can compare the ion to the atom. So the last one is trends in ionic size. So cations, so there's kind of two things happening here. There's cations and anions. So the cation is always smaller than the parent atom. Which means the sodium ion would be smaller than the sodium atom. Because when the sodium loses this electron to have a positive charge, it loses a whole energy level. So if you remember back to here, we're comparing the sodium ion to the sodium atom. The sodium atom is bigger because it has a whole other energy level. It has an electron in the 3s energy level. This doesn't even have a 3 energy level. So the sodium, any positively charged cation, is always smaller than its atom, than its parent atom. For an anion, anions are much larger than the parent atom. Because now we have an unequal number of protons for electrons, because we've added one more negative charge. When we add one more negative charge, it does not have another proton to be attracted to in the nucleus, because now there's one less proton than electron, which makes it negatively charged. So the electrons kind of repel each other a little bit. So the anion is bigger. So that means the fluoride ion would be bigger than the fluorine atom, because there's one more electron in this outermost shell. And now in this case, there's 10 electrons and there's only 9 protons in the nucleus for these 10 electrons to be attracted to. There's an unequal charge distribution. So now these electrons are going to kind of repel each other a little bit, which makes the anion bigger than the parent atom. So for periodic trends, I would expect you to be able to put elements in either increasing or decreasing order for ionization energy, electron affinity, and atomic size. And I would expect you to be able to tell me for ionic size, how the size of an ion compared to the size of the parent atom.